screen share. All right. Okay. I should be able to switch between these two. Okay. Set notation. You're going to have to have done the set notation. Are you all that? How do we feel about set notation? So if we're talking about the set, so this is what happens if you don't got questions wrong. All right, I'm going to have to make stuff up. Feel free to interrupt with ideas that things you might want to talk about. All right, or have a quick look and see if they actually released the like a practice sample test, because we could be talking about that too. But in the absence of stuff to talk about, like I say, I can sort of go through the notes, but that's going to make it a little bit more. That's sort of just trying to pick out the things that I think they might ask questions about. So if we just look at what this question is actually asking, in the list below, select the elements that belong to A intersection B without C. So the first thing we'd have to do with this is work out what elements are in B without C. So A is equal to 4 and Z. B is equal to Z, P, 9 and 5. And C is equal to. So another way of talking about B without C is sort of removing the intersection from B. So we're B, I'm going to change now. Now that I've got this thing written down, let's do this one. We're going to have to switch between these a bit, unfortunately. Where is a bit? That looks terrible. Okay. So B without C is, this would be the same as sort of doing B without B intersection C. All right. So the only bit that I'm taking out of B would be the intersection. And so when we start looking at the intersection of those two, so B intersection C would contain Z. P is not in this set. 9 is, so 9 is in both. And that would be it. And so when I do this B without C, so you can work out the same process, but just trying to sort of identify the bits that you're removing from the set can make it easier to work out what you're going to do. And so I've got Z, I've not got 9, so I've got P and 5. Now, that's all well and good. We're asked to find A union B without C. So now we've got the B without C part, and we're going to do the union. What's in both sets? Okay, and so we've got 4 and Z here. So it's got to be in one of the sets. So for Z, and P and 5. All right. Now, we can be quietly confident about that, right? Because we took out Z in that intersection, in that B without C, but it came back with the Z, with the A. All right. So we did the B without C first. That's why the brackets. And remember that brackets still applies in both situations. Okay. So we can definitely do that. Okay. Let's go and go. No, that one. All right. So we said 4, Z, 9, and 5. Not 9, P. We got one of those things where you've got to be careful about your handwriting, especially when you're inclined to make your letters look like numbers. What happens if we click this? Oh, okay. Did we let A be, select the elements which are in the set? Sure. Okay. Okay. Oh, next. That's what I'm looking for. Decide whether the following statement is true or false. All right. For all. So if you have trouble with these sort of statements, you've got those, that for all is what we call a qualifier. And so you actually, like I did this a lot with higher level maths, where you actually take that statement and you write out what it actually means. So for all x in Q, 20x plus 12 is an integer. All right. So does that sound like it's going to be true? No, doesn't really sound like it's going to be true. There will, so if that for all was changed to there exists, then it would be true. I could choose x in the rational numbers such that 20x plus 12 is an integer. All right, definitely could do that. Take a quarter. When I times by 20, I get 5. Thing works out for me. All right. But in this case, it's not. And so think about, if we're going to say it's not, all right, if we're going to say that it's false, we should be able to think of an example. All right. So if you're going, hey, if you've got a question like this in the exam, you're going to go, no, that's false. You can actually say, for example, if I choose 1/3. So 1/3 times by 20 is going to just get me 20/3 plus 12. Who knows? All right. 56 thirds. 56 thirds is still, 18 and 2/3. So there's still, it's not an integer, it's a rational number still. So we can definitely do that. And you can, so that by giving that example, you can actually work out what the possibilities are. Consider the function. Which of the following is the largest possible domain for f of x? Okay, love domains. First question we've got to ask when we're talking about domain is what restricts the domain? In this case, what restricts my domain? Square root. Thing out the square root is going to be positive. So literally the first thing I would be writing is I would be taking x plus 20 to 22 greater than or equal to 0. All right. And so I'm going to have x greater than or equal to minus 22. At that point in time, I notice that all of these options are written in interval notation. And so I'm going to try and write this in interval notation. And I'm going to show you that in a second, because that will make a lot more sense. So, and so you can see, start with x plus 22 greater than or equal to 0. Just a simple rearranging. Then I write that set in interval notation. Okay, so we've got, and because, so that's for the square root. There's another thing, wasn't there? Yeah. Yeah, that face looks like, hang on, you've forgotten something. Have I forgotten something? Yes. What did I forget? Yeah, it can't be 0. And so that means because it can't be 0, I've got to exclude the actual 22. All right, so now we know what the set we're looking for is. So when you have these multiple choice things, one of the best strategies is to not just go, look at these ones, is to actually work out what the answer actually is, and then select the thing that matches your answer. All right, because if you've done it right, your answer will be on the list. Okay, and if there's the option in which none of the above, and you go, hey, my answer is none of those things, you know in yourself that you've done the work to get it right, so you can actually calculate these things. So what we'll do is we'll go back. So we go here and we go minus 22 to infinity. That is an option. We feel happy about that. Yes. A function is defined by. Okay. So we've got a h of x, which is equal to so we've got something which is equal to x for x between minus 3 and 5, and minus 1 for x greater than 5. All right, sweet. So what is the range of the function? So well, the thing I do, and again, I would just go back to here and go, all right, if I've got this function here, what I'm going to do is I'm just going to roughly sketch it. So we know what x is between minus 3 and 5. So it's going to do that. It will go through the origin. It doesn't include minus 3, so I'm going to put a little circle here. It does include 5, so I'm going to color this in. And then it's going to be equal to minus 1 from everything greater than 5. Okay? Sweet. So from this, can we read off the range? Yeah, we can go. The range is just going to be minus 3 to 5. The minus 1 is included in that already. So the range for a piecewise defined function is the union of the ranges of each piece. All right. So I can work out the range of this piece just by drawing a graph. The graph is a nice and simple way to do it. I notice your thing says, I didn't think you were allowed a graphics calculator in the end. This is where I say it's actually your job to check that piece of information. All right. So you can't use a graphics calculator in the exam from what I've understood, but I want you to check for yourself. All right. Don't want to be thinking about these things too much. But this is a simple thing to graph. We all know how to graph these things. And so this should be, where's the thing? I could show that one. Should be able to do this. And so I want between minus 3 and 5. Notice how there's an option that doesn't include minus 3 and does include 5. So I can go, hey, that's going to be my option. All right, I wonder how many questions in this thing. Suppose f of x is equal to this, and suppose g of x is given by the table below. Okay, so actually, if I'd been thinking about this, composition would have been one of those things that I would have talked about. So when we do f composed of g, so f of x is equal to 3x plus 6. So when we do f composed of g as a function of x, give me a second. This is the same as saying f of g of x, all right? And so when I want to work out f of g of 12, this bit is in brackets, so I've got to work out the g of 12 first, and that's the number I'm putting in for x, okay? So this is actually one of those things where it might, I realize I might be talking to the good students in the class, but one of the things that quite often people make a lot of mistakes is that composition of functions. This means that I'm going to work out this bit first. It's literally in brackets, and we know we have to work out the thing in brackets first. So we're going to go back to the table. We're going to flick back to the table. Sorry for those people. I'm not sure how this is going to work. We have G of 12. So G of 12 from the table is equal to 4. I'm going to put question 5 up in the top corner there. And so I'm going to go back to doing my working. All right, so I've got my G of 12 is equal to 4. And so this thing here is going to become F of 4, which is 3 times 4 plus 6. 12 plus 6 is equal to 18. Really not loving this particular camera, but anyway. Not do anything about it today. And so, number. All right, we actually have to get into a number. What the? Okay, so, all right. You're all good with that? All right. So, like I said, I work better if you ask me questions. I will just make stuff up. I will just go through something like the sample test to try and find some questions to talk about. But if you've got questions, this is the point about doing this is giving you the opportunity to go, hey, I tried to do this. What should I have done? All right. Same goes for those people on the Zoom session. You can post questions in the chat and I will talk about them. All right. Woohoo. So I am not looking at that, am I? No, I am. Beautiful. So let f of x be the function with the graph, blah. Which of the following? So again, graphically, what do we know about the inverse of the function? Sweet. It's like the reflection along the y is equal to x. So what I'm going to do is I'm going to try and copy this down. Copy the graph down as close as I can manage. And so it went through 1 there. This looks like an exponential function. All right. So then I'm going to do a thing where I put in y is equal to x. All right. And so we're going to do the inverse. It should look like this. We notice asymptotic behavior around here, so we're going to try and make it look like that here. And we're going to try and do that. Because our original function looked like a exponential function, loosely, our inverse is going to look like a log function. So we've now got a picture of what that's going to look like in our head. So this is that idea. We've got a multiple choice question. We actually draw out what we think it is first, and then we see if we can find it on the list. All right, let's go to the list. With that in mind, and me not knowing exactly how to... All right, there is only one of these, which is this one, that looks like it's actually anything like what we're talking about, right? So we can go, all right, we can be quietly happy about that. The idea that that while we're doing that, that this is going to work. Remember that when we're talking about sort of f of x, if I do f of x composed with sort of f inverse of x, that should give me sort of, it actually just gives me the identity. It's like a polynomial identity. So we're working in a functional space, and the inverse is the thing that I compose together. So to make it, so if I do f composed of f inverse, you'll see in the notes it sort of says f inverse composed of f is just going to be equal to x. It's just the variable, right? Because so when we do these abstract things, I'm gonna talk for a second. When mathematicians came along, they're like, we love numbers, right? Love numbers. Numbers are great. What else in the world can act in the same way as numbers? All right. And so we're going, all right, we've got functions. Functions are cool things to do with numbers. Can I talk about functions in the same way I talk about numbers? And so we've got a sensible way to add and subtract functions. All right. We just, for every value of x, we just add the function values. That makes sense, right? You've all seen polynomials where you've got, you know, x squared plus 3x plus 1. you know that you work out this value, this value, this value, and add those numbers up. You could write that as a sum of separate functions. So we've gone, okay, well, we can do ordinary multiplication. That makes sense. All right. And then, so with some functions, there's a division. That's where you get those rational functions. That makes sense. Can we go to the next step? Can we compose these? Can I put one of these functions inside the other? And the first question you've got to ask, well, the first thing that we ask is, if I do that, can I undo it, right? You think, we had addition, everybody fell in love with addition, and they're like, but can I undo it? And that's where subtraction came from. We're then going, hey, if we do lots of addition to the same number, there must be an easy way to do that. That gives us multiplication. Can we undo it? That's where we got division from. So in the same way as we're doing, hey, I've got this cool thing where I can put a function inside a function. Can I undo that? And that's where we came up with the idea of doing inverse functions. And so when we're talking about how we came up with those inverse functions, we've then gone, okay, when does it apply? Because we've then gone, hang on, not all of the functions can I do this for. And so that's one of those things where we've actually started to go, when do we talk about doing this? Now, I don't actually recall the thing talking about the conditions under which we have an inverse function. You guys talking about doing inverse? What's that? We did the one-to-one and onto thing. Yeah, cool. So we're going to just, which one are we looking at? That one. Let's go. So one of the things when we're doing, when we're talking about what one is, so F inverse. Well, they quite often write just 1, 2, 1. Oh man, that's terrible. I'm sorry, this camera just is terrible. Sure. Can you still read that? Yeah, okay. I'm gonna. So we can actually check that, and so. So you guys have all heard about the horizontal line test? Good. Yeah. That thing where I did, because I flicked through the notes last night and spent like 3 hours flicking through the notes because there's a fair bit of notes. But there are some things I didn't actually I've gone, they're doing inverse function things. They will have done this, and I forgot to check some of the details that I might have wanted to talk about. So I noticed at the very start of the course, you talked about what makes a function, right? So one of the things that we might know is when you get a function, there's this horrible definition that if it's a function, then f of x1 is equal to f of x2. No, for every x, there is only one value for f of x. All right, and that's where we come in. That's where we actually have a thing called a vertical line. So if I draw a vertical line through any relation, and it goes through, that line passes through the relation twice, more than once, then that makes it not a function. The horizontal line test is that doing that inverse. We're actually going, can I check that this would be a function if I did the inverse function? If I flipped it on, if I actually did that reflection in the line y is equal to x, would it pass this being a function, right? Right, so you think about it. I did a vertical line test to check if it was a function. I reflected that test in the line y is equal to x to get myself a horizontal line test to see if the inverse would be a function. And that's the thing that helped me determine if the inverse would actually be a function. Yeah? Loving the plan? All right, so that can help you remember what's going to happen in that situation, okay? Yeah? All right, sweet. So, I'm going to go back to this thing. So we did that. Everybody's happy with that. Summation. That was, I'm going to go, I'm going to try and okay, summation. With this sort of thing, so we've got tricks, all right? My favorite phrase for, if you ask David, I will say, write them out, add them up, all right? It's a sum. You know what to do with these things, all right? There's a bit of a thing which says, if the number of numbers is less than about somewhere between 6 and 10, you could just write them all out, add them all up, because you can do that because you're a math student. All right, not that hard, people. We can write them out, we can add them up. If there's more than about 10, more than about 6 numbers, there is possibly a trick. All right. You will notice these sums say from I is equal to 5 to 21 or I is equal to 1 to 21. Oh man. So I'm going to write these things down before I get too far, and then I'll show you what I'm going to do. Summation 21, I is equal to 5, AI is equal to 10, summation I is equal to 1 to 21, AI is equal to 20. And so find, determine, whatever you want to call it, I is equal to 1 to 4. All right, notice how we've been given no actual numbers. All right. But this thing here, so I've actually got to do a trick. Let's do this. Swap it over people's. All right, sweet. So if I look at this sum I is equal to 5 to 21 of AI, that's equal to A5 plus A6 plus, there's a lot of other numbers, plus A21. So when I say write it out and add them up, quite often what I mean is write out the first couple, write out the last one or two, so you know where your sum starts, where your sum finishes, all right? And so this, and we know that's equal to 10. If we do the sum 21, I is equal to 1 of AI, that's going to be like A1 plus A2 plus, in this case, I'm going to go, oh, that's going to get to A4 plus A5 plus A21. All right. Notice this bit here is different from this bit here. If I was to have these things, I could do, oh, if I do this one, take this one, I would work out what those 4 numbers are. Literally, if I do this thing here, this one here, take this one here, I would be left with those 4 numbers. Those are clearly the difference in those 2 things, because all these other numbers are going to cancel out. Yeah, love the plan. So this is my idea. We bring it back to sums, because we've been doing sums since we were like, you might think it's like grade 1, grade 2, grade 3 maybe, depending on which school you went to. I don't really know, because it's been a long time since I was in primary school. So what I can do is I can go, well, A1 plus A2 plus A3 plus A4 is going to be equal to sum I is equal to 1 to 21 of AI minus sum I is equal to 1 to 5 to 21 of AI, which is equal to, we said this one was 20 and this one was 10, and so it's going to be equal to 10. These 4 numbers add up to 10. Sweet. I feel like, okay, that's good, but that's not exactly what we're asked to do yet, is it? No? So if I go back up to what we were asked to do, I is equal to 1 to 4 of 2 minus AI, I'm just going to write that all out. It's like 2 minus A1 plus 2 minus A2 plus 2 minus A3 plus 2 minus A4. So I'm going to go 2 plus 2 plus 2 plus 2 minus. So this is, right, hashtag, would not actually recommend you necessarily do that in exam. However, we should point out that while I'm explaining what I'm doing and doing this at the same time, I still have not taken more time than you've been allotted for this question in an exam, okay? So you can just do this. All right. Too many people think I have to figure it out without writing stuff down, when the right advice in an exam is write stuff down. If you have written this and you got that, if you left it there, they may well go, you're basically there. I'm going to give you that mark. All right. They may not, depending on how they're feeling on the day, but you've written stuff down. They've got something that they can give you a mark for. All right. So you can go, this is going to be 8. And we decided this is 10 minus 2. All right, so we can actually do that. So, so very easy, very quickly get an answer. Don't be afraid to actually write out lots of, like, we're quick. We can actually write this stuff out quickly if we decide to do it. Most students in maths exams sit there and twiddle their pen, trying to work out what the right thing to do is. If you start writing something down, I had really bizarre. I had a student who wasn't very good, but they embraced writing stuff down very quickly. And it made a huge difference to what they did. All right. Find this. So we've got sum I is equal to 1 to 6 of the sum j is equal to 1 to 9 of 0.5. This is question 8. Woohoo! Anyone want to guess what that number is? All right, I'm going to put my hand up and say I think it's 27. Yeah? All right, what did you do? Yeah. Do with the others. All right, so what you're saying is, I'm going to switch to writing this down. So you're saying we're going to actually work out, we're going to do 6i is equal to 1, and then we're just going to focus on sum j is equal to 1 to 9 of 0.5. So again, if I wanted to, I could do the write it out, add it up. I is equal to 1 to 6, and this would be 0.5 plus 0.5 plus 0.5. There are 9 of them. That's literally 0.5 times by 9. And so I'm going to go sum of I is equal to 1 to 6. 9 times 0.5 is 4.5. So again, I could do that thing where I go, oh, that's going to be 4.5 plus 4.5 plus 4.5, which is going to be, well, 4.5 times by 6. And that's where we came up with 27. Okay? For an exam question, if you have to write stuff down, you write that. Took almost no time. Now, admittedly, there was pretty much everyone in the room going, yeah, okay, 27 is the right answer. But writing stuff down gives you something, gives you an opportunity to sort of investigate your thinking. I'm really bad for this, right? I've never actually got 90% or better in an exam, because I don't stop and write stuff down and think carefully when I'm in an exam. My brain wanders off and I go, oh, I'll just do this. I know what I'm doing. I'm really smart, which is not true. All right. The poster child will write stuff down. All right. I lost 5 marks in the exam, last exam I did, for not writing it down straight away. I gone, oh, it should be this. And also I lost 5 marks for writing the wrong letter from the multiple choice questions, because I get my B's and D's confused. And so I just gonna stop crying about that. It's only been like, no, won't talk about the number of years it's been. Okay, so suppose you are on holiday and you are packing your suitcase. You have 15 books and you want to choose 4 of them to take away. How many different choices are possible? Okay. So, are we assuming these items are distinct? All right, because it's not like we're taking writing pads and they all look the same. So, because at some point in time you go, it would make no difference. So we've got different books, you know, Treasure Island, I don't know, you know, Jane Austen, what is it, Pride and Prejudice, Wuthering Heights, whatever. You got your books, you got your favorite books. So I'm going to do this because I wrote this out yesterday. So we have this thing here. So the question is, which one of these formula would be the right one. All right. We've got 15 items. Now, one of the things is down here where it says permutations, order is important, and combinations, order is not important. Is the order these things go into my suitcase important? No. So that sounds like we're choosing combinations. All right. Is there repetition or is there not? There is no repetition. We're assuming we're not going to choose two copies of, Wuthering Heights. So we're down here, and this is the straight combinations. And so we can actually, so in terms of trying to talk about what your thinking is, right? So with every one of these things, we want to sort of have some reason for how we chose this. I don't actually recommend you try and memorize that. So this fancy notation is just talking about the binomial coefficient. All right, there are 15 items. I'm literally choosing 4 of them. All right, that's all it is. So unfortunately, this is sort of one of those things where you go, okay, I have distinct items, the order doesn't matter, therefore this is going to be the right answer. All right, so it can be that simple. I wonder if I'm about to run out of time. I wonder how many questions in this sample test. All right. On a rainy day with nothing better to do than to decide and to place 50 identical marbles into 3 different boxes, 3 numbered boxes, with no restrictions. So boxes can be empty. What formula would, and the number of ways to do this? Oh man. Okay. So I believe, did they talk about stars and bars? So what we're going to do, 50 marbles is a lot of marbles, all right? And so we can't actually do that, all right? So if I was to try and think about what's going to happen, right? I'm going to take a bit longer than this question's than it's allotted for this question to do this. So I'm going to talk about something which is not actually the answer, right? But it's about trying to motivate how you could think about this, right? If I have 50 marbles, so I have my boxes. I have my 3 boxes and my 50 marbles. I'm not going to try and draw 50 marbles. What I could do is I could decide I'm going to put them all into 1 cup. All right. And so I'd have 3 choices. Or if I decide I'm going to put them into 2 cups, that gets a bit more complicated, all right? But I'm actually deliberately choosing 2 non-empty cups, all right? And so one has to go here, 49 here, 2, 48, 3, 47, so on and so forth. So the number goes from 1 to 49 for one of those cups, all right? And so that means there's actually going to be, what does that mean? 49 possible ways. But then I come to choosing, but I've got to times that by 3, choose 2. I've got to choose 2 of those cups. All right. And so all right. And so then I can go through and go, well, I could actually go, let's just have none of them empty. All right. So I could start by putting a marble in each of them. But then I could just do that same process with the fewer number of marbles, couldn't I? All right. Okay. Sounds like a great plan, but it also sounds like it's going to be difficult. Okay, so let's simplify this thing down. So I could go all this way. Maybe what I'm going to do is maybe this putting marbles into distinct objects is not actually as sort of, it's not the same, right? Maybe what I've got is I've got a big trap where I line my 50 marbles up, and I'm going to separate them. I've got special blocks that sit on the trap that will separate these things, which are like another space. All right. So if I go, maybe I'm going to try and do this with, say, 7 marbles. Sorry. So I've got myself a track. All right. And then I'm going to put up a spacer. And then I'm going to put another spacer. And so I could do that. This trick with working out where to put these extra spots comes down to choosing 2 spots out of all of these possible spots, all right? So if I go back to, where's my thing? Where did we put it? That one. I go back to this thing here. I got this funky formula. So the order of these things, because they're identical, doesn't matter. That's actually one of those tricks. But this means I'm down to these combinations, but with repetition. And you notice this has got this formula, which is like R plus N minus 1, choose R. This comes down to, I have my 7 things, I have 2 spaces, which count as the number of things. That's at N minus 1, all right? Because I've created 3 separate piles by doing this, all right? And so this is the thing that tells me, okay, I just want to choose where I put them in the list, all right? So I want to separate my 3 groups by putting spaces. Now, there is nothing stopping me putting my 2 spaces at one end and then putting my 7 marbles, which would be equivalent to all of these going into one bucket, all right? So at the moment, this would make 3 into this one, 2 into this one, 2 into this one. But if I do this, this would be saying, actually, I'm going to put all of them into this bucket. All right. And so this is where that formula, where you go R plus and then N minus 1. So number of spaces, number of places minus 1. And then choose, well, so we've got N minus 1. Or, so I'm either choosing where I put the spaces, or, and equivalently, R plus N minus 1, R. And so that would be choosing where I put the marbles. Yeah. So that's a way to think about this problem, to sort of talk about what's going to happen with these things. All right. There's lots of ways to talk about these things. So the point about doing this bit up here is you could actually go through this. If it wasn't 50 marbles, you could go, hey, I could do this. Or I might be able to notice a pattern about what's going to happen here. All right. I might be able to go, oh, this happens. And I could create a sum and I could do that this way. I have actually done that in the past and come up with basically the same thing as that, algebraically equivalent expression. So talk to yourself about the story that's involved in what's doing it so that you can actually make these things happen for yourself. Okay, so we came up with, so in this case, our R was equal to 50, our N was equal to 3, and so correct options would be 52, choose 2, or 52, choose 50. I'm going to swap back. And so you'll see 50 choose 50. Ah, I did get that right. Ooh, there is only one of them. I thought there was going to be 2 correct answers, but I was wrong. Okay, so we can do this, yeah? By thinking about what the situation is that you're dealing with. The reason they call this, so sometimes they refer to this technique as a stars and bars technique, because you can think of that, you've got your stars and you've got your bars separating your stars. Or in this case, you've got marbles and you've got something that looks like stars to separate them into their groups. All right. So into distinct buckets means that they're necessarily, they have an order to them. Okay. All right. Oh, it's going to cut. Oh, man, that's not cool. 10 out of 16. See, I talk too much. My apologies. Okay. Again, I'm just going to pause since we've been about an hour into this. No, I want that one. Does anyone have any questions that they particularly wanted me to talk about? No? Sure. What that? Conditional probability? Sure. What did you get told about? Oh. Bayes theorem? Did I put it down? Did I actually know which one was Bayes theorem? Okay. So that's two. There was one. Three is times differentiation. Yep. Okay. So I'm not sure how well this comes up. So you notice down the bottom here, there's a couple of things. Some of this stuff is just leading. So some of this stuff we're going to sort of talk about just quickly to sort of go, this is actually where we start with this discussion. All right. And so you notice that we got probability axioms. So there's a whole lot of probability axioms. Probabilities have got to be greater than 0 and less than 1. If probability is 0, then it's never going to happen. If the probability is 1, it's always going to happen. Sum of all probabilities has to be equal to 1. So I noticed there was a bit about discrete probability distributions. So the sum of all my probabilities has got to be equal to 1. We're going to start working with some of those ideas. There's also, the Morgan's law is actually about sets as much as probabilities, all right? So with probability, we work out the probability of events in a particular set occurring. So that's why the first part of this, there was a lot of talk about what set notation is. And actually understanding sets well is actually a very big part of understanding mathematics, and also where it's really important for data science, right? So understanding your sets, what constitutes an event, etc., is actually really important for data science. So you're going to do programming, and you're going to want to have your sort of conditional statement, and you need to make sure your conditional statement covers every possibility. All right. Now, I know with programming, there's a thing called an exception, or you cover all at the end. If we didn't get caught by any one of these cases, let's just do this thing. But we want to be sure that we're covering all possible cases, all right? Because otherwise there might be something important that we haven't thought about, all right? So that's why things like, these are just working with complements of sets, all right? That's actually one of those things. The next part about this, and the reason I've got this, I started on this page, is actually when we talk about independent events. So the whole point about independent events is the probability of one occurring does not, so knowing whether one of these events occur does not change the probability of the other. So when we see that thing, this thing here, where it says, this literally says the probability of A given B, all right? And we're saying that if the probability of A, given that we know B has occurred, is the same as just the probability of A, then we know those are independent events, okay? One of the things we use that for is we've got this probability of A and B. It's just the probability of A and the probability of B. So if I have two independent events, the probability they both occur is just the product of the probabilities. And there's a thing called the multiplication principle that would cover that particular outcome. Okay. So actually what can be a really funny example? So just on sort of, what's that? No, I don't think so.
Someone out of Zoom.
Oh, that would be David then.
No, check.
Okay.
And then is there anyone in the chat?
Um,
Are you recording?
we look like we're still recording, and we still have someone in the chat, and so yes. All right. So okay, we know. Thank you, Dr. Roberts. What was I saying? There was a thing I was going. There was a point I was going with that. Independent events, blah, 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 blah. Oh, yes, I know what I was doing. Okay, so what you can do is if I take the numbers, I'm going to start by doing this. If I take the numbers 1, 2, 3, up to 15, right? And A is the events. All right, so if I do this thing where I go, I take these numbers 1 up to 15 and take the event A, probability divisible by 3, probability B, probably the event that the number is divisible by 5. Then, all right, I can do my probability of A is equal to, there's going to be 5 numbers, 3, 6, 9, 12, 15, 5 numbers. This is going to be 5 on 15, which is going to be equal to just 1 on 3. Kind of feels good, doesn't it? You kind of feel that like the thing. Probability of B, I'm going to spend a little bit less time and go, hey, that's going to be 3 on 15. It's equal to 1 on 5. We can be happy with that. Now, if we think about probability of A intersection B, there's only one number, isn't there? That's like 1 on 15. Also going to observe probability of A times by probability of B is equal to 1 on 3 times by 1 on 5. Multiply numerators, multiply denominators. I get the same number. All right. This means that these events A and B are independent. Yes, loving the plan. So, all right. A and B independent. If you're asked to show that events are independent, that's what you would do. All right. If I take my set, if I change my U, 1, 2, 3, I'm going to stop at 16. And I'm going to do this bit again. Probability is now just going to be 5 on 16. Probability of A, that would help. Probability of B would be 3 on 16. And probability of A intersection B is still 1 on, it's now 1 on 16. If I do probability of A times by probability of B, that's going to be like 5 on 16 times by 3 on 16. That's going to be 15 on 16 times 16. This is now no longer equal. All right. You would think things divisible by 5 or being divisible by 3 would always be independent, wouldn't it? All right. But this is just one of those peculiarities that happens with creating a finite set to deal from. And so we've got to be a little bit careful about when we're doing this. So if the question actually asks you to check that they're independent, doing this calculation is actually, you kind of need to do it just to check, because it's possible. So some things which you would expect to be highly dependent events can be independent based on the probabilities you work out, and some of them can be, where you expect them to be independent, can actually work out to be dependent. It's important that you actually go through and check. Okay. All right. Cool. Now, point made. So, so there's two parts. There's two parts. I'm not sure which part you wanted to talk about that comes under the heading of Bayes' law. There's sort of this. So this is changing the conditional probability. And there's this thing here. This thing here, which is actually what I think of as Bayes' law. Yeah. So when we talk about what this is saying, all right, we're using these BIs, all those smaller sets B, to create what we call a partition. Have you talked about partitioning? No. Right, sure. Old-fashioned word. I'm old. There's words for being old. So when we've got when we've got a universal set, I can break it up into bits. All right. And one of the things that would be really good for my bits is for them to be mutually exclusive. So we're all comfortable with the term mutually exclusive? Yeah, no, maybe. Gonna say that's a no, Nick. All right, so I'm just gonna put down. All right, so if I have mutually exclusive events, all right, what that means is if I know this event happens, this event cannot happen. All right, and so that would be A intersection B must always be the empty set. Okay. Now, so if I have my sets mutually exclusive, and so there's this thing. There's probably a better way of putting that. That doesn't use terminology that you may not have heard before. We could say a little bit more clumsy. For all x in U, x is in BI, and x not in BJ, I not equal to J. So we're saying for every x in the universal set, it's in one of the BIs, but only one. So this is a really useful property you have for your sets. All right. You want to be able to have this property. And so what we were saying when we were talking about let's try and do it there. What we're trying to do with this sort of thing is there's actually a set property. All right. So I can go, okay, so the set A would be equal to sort of A intersection B1 union with A intersection B2 union A intersection B3 union union A intersection Bn. All right. So I can have this thing where all the bits of A are in one of these B's. All right. Once I've got all these B's, making sure, so because everything in the universal set is in one of the B's and only one of the B's, possibly what I really should have done here is gone BI intersection BJ is equal to the empty set. I'll get it down here so we can, is equal to the empty set. I is not equal to J. All right. So if I have different ones of these B's, their intersection is empty. Okay. So that's that mutually exclusive. And so if I apply that term to a lot of sets, I'm saying none of those sets have any intersection. All right. And so creating this lot of sets. And so what this law is saying here, when I have this thing that says, so when I go probability of A, I can do this thing where I basically exploit this idea. So remember, the union is like the addition. And so this is probability of A intersection B1 plus probability of A intersection B2 plus so on and so forth, plus probability of A intersection Bn. Now, all right, we're feeling happy about this. But if we go back to some of these things about, if we go back up to this idea here, when we go, I want to put when I'm putting this down as probability of B given A is equal to probability of A given B times by probability of B on probability of A. All right. Okay. Awesome. If I take this idea and rather than treating B as just one set, I treat it as that whole partition of sets. All right. So we can go probability of BI given A would be equal to, so this is going to be probability of A given BI times by the probability of BI all on, and so sum, this bottom bit is going to be, we're going to write like this, sum of, except for, we're going to do it as the conditional notation. That should be a K, because it needs to be a different letter. So this is just saying this thing here. So in the same way as it's saying the same thing. But what we're doing is, rather than we're talking about just swapping around the conditional probability of A and B, we've got lots of parts of B. And we're going, actually, I can work out the probability of any one part of B given A if I know the probability of A given that part of B. So that's what this thing is saying. Now, all right, so we get told this. There's very few things that you actually do with it. One of the biggest things you do with this version of the conditional probability thing is that we've all seen that. Well, have you? Oh, about to go. You would have seen it, but then I go, actually, maybe not. So we all know about, like, we've all done the rapid antigen test for COVID. We've all done way too many of them in our life. But they have two things that they talk about. There's like an accuracy and a specificity. And so these terms refer to the rate of false positive and the rate of false negative. All right. And so we can actually go through there's a bit of a paradox that comes about by having these things, right? Your test might be sort of say 90% accurate and have like I have trouble saying the word. I think it's specificity. Yeah. Term meaning the rate of false negatives. That they can be quite high numbers, but you can actually, they seem like it's going to be like, the probability that any one test gives you a false negative can be quite high. and you know, can be nearly 1. Rate it gives you a false positive, can be really high. Because the probability of having a particular condition can be quite low, you can get the probability of having the disease given you test positive can be quite low. So let's go back to the heyday of, let's go back a little bit and pretend, so we probability of having the disease. All right, in the population. I'm going to go, let's say it's only 1%, 0.01. All right, for argument's sake. Probability of testing positive, given you have the disease. So these tests, quite good. So the probability I test positive, given I have the disease, is 0.1. Probability test positive, given I don't have the disease. All right. Now, so this is that thing that can be quite low. I'm going to say that's only, I don't know, let's say 5%. So 0.05. All right. The thing I want to know, though, is I want to know the probability of having the disease given I tested positive. So that's where this idea comes in. We're going to try and rearrange that conditional probability to work out what these things are. Now, one of the other things I missed, yeah, it's actually in there, but it's on page 1, no, page 2. Total probabilities. So, because my D and my G complement do this partition, they're mutually exclusive, but you either have the disease or you don't have the disease, right? There is no, maybe have the disease, maybe don't. There's no middle ground here. You either do or you don't. And so one of the beautiful things is I can go, probability I test positive is probability I test positive given I have the disease plus probability I test positive given I don't have the disease. Did I do this right? Oh, I used the wrong thing. Oh no, right, my bad. Wrong thing. Probability I test positive given I have the disease times by the probability of having the disease plus probability I test positive given I don't have the disease times by the probability of not having the disease. Sweet, good. That's what I needed to do. So this thing here is just going to write this underneath. This is probability of testing positive and having the disease, and this thing here is the probability of testing positive and not having the disease. Okay, so these things, whoops. These things, we can sort of think about them in this way, all right? Cool plan. Now, we've got most of these numbers, or we can apply them. What I do, though, my favorite plan, all right, I have a favorite plan. I have favorite plans all over the place, is we're going to try and do this, right? We're going to go, okay, because these are conditional probabilities based on the disease, this is disease, this is not having the disease. You have talked about tree diagrams, and so we should do tree diagrams. And so this is like test positive and test negative, test positive, test negative. Right. We have these numbers. Well, we've sort of made these, admittedly, I've made these numbers up. But if we're saying this is 0.01, this has got to be 0.99. All right, fair enough. All good with that. So we said probability I test positive given I have the disease. So this is saying I've got the disease. This probability is going to be 0.98. And so those two have got a sum to 1. So this is 0.02. You've seen this sort of thing before? Yeah? All right. So my plan is always when you're given conditional probabilities love a tree diagram. All right. And so we really want to go the tree diagram. And so in a similar way, we test positive. So this is like a 0.05 and this is a 0.95. All right, sure. Got the thing happening. Okay. Now, if I multiply, so see how this is like this number and this is this number? Wow, not quite, is it? All right, so this number, so this thing here, if I multiply it together, that's going to be 0.0098. Going to be a small probability of testing positive and having the disease. All right, only slightly smaller than the probability. So I can actually, and this would be, so T intersection D. And so each one of these could be considered as, so this would be like T complement intersection D. This one here would work out to be sort of T intersection D complement, and this one would be T complement intersection D complement. I can work out all of these values from that tree diagram. All right, so each one of those branches, if I multiply along the branch, gives me the intersection of those two events happening. All right, and that can be a really useful way to think about what's going on with this question. All right, getting back to what we were trying to do. So we were going to try and do this thing where we go back up this here. We were going to try and use this identity. So we're going to try and use Bayes' law to rearrange to get the thing that we want. All right. So we want to go, because we want this, so we want probability of D given T. All right. So D is where it would be. So probability of T given D times by probability of D on probability of T. All right. You will notice that I very carefully told us what to do about calculating this probability. And so I needed to work out this one here and this one here. So this is going to be, this one here is going to work out to be 0.04995. I reckon. I'm going to pretend I'm right. And so when I add those two probabilities up, so my probability of T is going to be probability of T intersection D plus probability of T intersection D complement, which I am trying to tell you is 0.0098 plus 0.0495, which would be 0.0593. All right, let's pretend. Really should have brought a calculator at some point in time. Here's the thing. Calculator is no longer a thing in my life. And so we've got my numbers on. So this is the number in the denominator. So my probability of D given T is going to be equal to, so what did we say this number was? I said that was 0.98, and I'm going to problem times by 0.01 on 0.0593. And so we reckon that's going to be 0.0098 on 0.0593. At this point in time, my favorite pastime to actually calculate numbers, because owning a calculator is a bad idea. Go on. There are days oh, I think about it now. It'll be fine. All right. All right. It is eventually going to do this. I'm going to say approximately 0.116. All right, but let's just do this. Now, all right, so we know that when we want to do a calculation in Excel, we start with an equal sign. So I actually want to repeat some of these calculations just to make sure I've got it right. So I want to do 0.98 plus by 0. Where was I? Now 0.0.01. That's going to be one number. All right. And we want to do the other one. 0.9 times by 0.05. All right. So the number we're talking about is literally that top line, that number, divided by, and then that number again, plus the other one, 16%. Okay, this number. So the problem, so I've done my fancy test, right? Rate of false positive is like only 2%. Rate of false negative is only 5%. Sounds like a good thing, doesn't it? I get my test back and it says I'm positive. I test positive. It's only a 16% probability that I've actually got the disease. All right. So this is one of those tricks about conditional probabilities with these things. It's kind of like a paradox. There's the probability with the probability of actually having the disease being sufficiently low. There is the rate of false positives, that the effective rate of false positives is much higher. All right. That's why, we can do all sorts of tests, but it's actually better to know if you have the disease or not. So yeah, so this is actually a really good thing. This is actually also on the heading of things that are likely to come up in the exam. All right. So, all right, cool. Anyone else got questions? All right, I'm gonna reiterate the bit where it makes my life easier to have your questions rather than me trying to talk about stuff. Taylor series. We should do some of the standard Taylor series. Have you guys got enough of that down? Yep. So Taylor series is actually a really good thing to talk about, actually. Now everybody wants to talk about Taylor series, right? Because Taylor series are a little bit tricky. And the first thing we've got to remember about Taylor series. Thank you. Do not feel afraid to go, Nick, you have not changed what the camera's looking at, because I forget all the time to do that. All right. And I'm aware that when I'm talking in front of a class, my brain is thinking about 4 or 5 things, and one of them should be whether I'm actually showing you what I'm talking about. But hey. So what I'm going to do, I'm actually going to do a couple of Taylor series. All right. And then I'm going to talk about some of the tricks we use with Taylor series. All right. So I'm going to try and do like e to the x. E to the x is nice and easy. Maybe we'll do fruitcake. Or I'm going to run to the office because I forgot to grab my power supply. All right, how about we go 5-minute pause while I run to the office and grab my power supply? Yeah. And I will be back shortly. All right. Oh, After. Okay, so the reason I'm going to do, I think we'll start by doing e to the x. Firstly, I want to show you how you should do a Taylor series. Like if you're asked to do a Taylor polynomial, and that is an extremely likely thing to happen, what the first thing we should do is work. So if we're going to take f of x is equal to e to the x, we're going to create ourselves a little table. I'm actually going to do the Maclaurin polynomial for e to the x and sine x. And then I might pick on something else we might try and pick on something else to do for a general one. All right. So what we're going to do, we're going to go, all right. So I've got e to the x, so that's f of x. The reason I'm doing this one is it's nice and easy. F of x, f double dash of x, they're all e to the x. And so x is equal to 0. So I'm creating this little table of values, all right? And these numbers are all 1. Okay, so I've got this nice thing happening here, right? They're all 1. My Taylor polynomial, so my Taylor polynomial degree n is some I is equal to 1, 0 to n, f of f, the ith derivative evaluated at, I'm going to say a and then do that x minus a on n factorial. I. They should be i's. All right. The reason we create the table is this is these numbers, right? So this is going to be like f0 plus f dashed of 0 times by x, technically on 1 factorial, plus f double dashed of 0 on 2 factorial x squared plus dot dot dot. This one here, so this is going to be, this number is 1, this number is 1, this number is 1. So this is going to be plus x, and then this is going to be plus x squared on 2, plus x to the x3 on, I'm going to put in 3 factorial is just 6, plus x4, 4 factorial is 24, plus x to 5 on 5 factorial, 120. All right, dot, dot, dot. So sometimes we can actually recognize the function that we're dealing with, okay? And so they kind of, it's not sort of said, oh, you should be able to recognize the Taylor series for the e to the x, but also they kind of to sort of go, you should be able to recognize the Taylor series for e to the x. So awesome, that's great. If I do say sine of x, and so cosine of x, hang on, whoops, wrong, well, one step out. Sine of x, so my function is sine of x, my derivative is cosine of x, my second derivative minus sine of x, and then minus cosine of x, and then I'm back to where I started, all right? And when I evaluate those at 0, I get 0, 1, 0, minus 1. So I've got this sort of pattern. So I'm going to go for the Taylor series for the exponential, Taylor series for sine. And so I'm going to just jump into this form here. Whoops, we didn't see that, did we? No. This is that thing where you go, hey, Nick, you didn't show me what you were writing down. And so these numbers are nice, simple numbers, right? And they've got this pattern, 0, 1, 0, minus 1, 0, 1, 0, minus 1. And you can just see it happen, all right? So if I write that out, all right, so because I've got this number is 0 plus 1 times x plus 0 times x squared on 2 factorial plus minus 1 times x cubed on 3 factorial plus 0 times x4 on 4 factorial. You kind of have to go a little bit further. And so what I'm getting is going to be x minus x cubed on 6 plus, whoops. Yeah, good. Please do. X to the 5 on 5 factorial. And then I'm going to go minus, so this will be x to the 7 on 7 factorial. Maybe at this point in time, I'm going to say 7 factorial. But notice that, so like what we've done is we've picked out the odd powers out of e to the x, but we've changed the sign on every second one. All right. And so this thing has a horrible expression. So actually, if I try and write this in summation notation, I is equal to 1 to n. To get this, so to get the alternating power, I do minus 1 to the power I. And then I do x to the 2i minus 1. We're going to have to, I've left a little bit of room here because I want to make sure I've done the right power. 2i minus 1 factorial. Okay, so at this point in time, I go, well, if I is equal to 1, that will give me x, and this needs to be positive. So what I'm going to do is I'm going to go plus 1 to make it so I've got the right sign. All right, slick. I know now there's a reason I'm actually writing this down, because again, like exponential functions, the sine one is one we might expect you to sort of half recognize. Okay, so we might expect you. So if you've got a bit of an idea of what it's going to look like, and so while we're doing this, all right, let's change this around again. What I'm going to do is you can sort of see what I'm doing with these, right? And so if I was to do the Taylor polynomial for cosine of x, all right, going to start 1 plus x squared on 2 plus minus. Then plus x to 4 on 24 minus x to 6 on, let's say 6 factorial. So there's this thing again with that alternating sign happening, but also these are just terms that look like they came straight out of the exponential function. Yeah? There's it. funky thing happening with that. These are, so the terms look very similar to what's going on, okay? And it's worth being aware that that's actually happening. So, right, so there are two things we like to ask you about Taylor polynomials. All right, Taylor polynomials. There is composition of functions applying to Taylor polynomials. So Taylor's theorem, I'm going to ignore a bit of the crap, but Taylor's theorem says that f of x is equal to the polynomial plus a remainder polynomial. All right. It says equals. All right. So that means those things are equivalent. Those expressions on either side of that equal sign are equivalent equal signs. All right. So if I was to do e to the x squared, all right, that would be like e to the x composed with x squared, wouldn't it? If I treat that as functional composition, right? If I go f of x is equal to e to the x and g of x is equal to x squared, e to the x squared is just f composed of g as a function of x. Sure? We're comfortable with that plan? If I want the Taylor polynomial e to the x squared, I can do the composition of functions. Yeah? So, I've got my Taylor polynomial. Let's bring it down. Can we see it there? Taylor polynomial here. So what I'm going to do is my Taylor polynomial for e to the x is equal to 1 plus x squared on 2 plus dot. So Taylor polynomial for e to the x squared is just this 1 plus x squared plus x squared on 2 plus x squared cubed on 3 factorial plus x squared power 4 on 4 factorial, so on and so forth. That would make a lot more sense. Yes, we will expect you in the exam to know how to do that. All right, to recognize that I already know a Taylor polynomial. You'll know this because quite often the question will say, what is the Taylor polynomial for, say, e to the x? Now, hence, deduce the Taylor polynomial for e to the x squared. If you were to do the differentiation for e to the x squared, it gets very messy very quickly. Very messy very quickly. All right? But this was not hard at all, was it? This was a walk in the park. All right? So I've seen them do things where it's like, just sine of 2x. Same principle. I replace x with 2x in that expression for the Taylor polynomial, and I get an answer straight away. Okay? How clever is that? Yeah, that is, so it is a thing we expect you to know and be able to do. Okay? So the other thing, did you talk about radius of convergence? Power series radius of convergence? I didn't notice it in the notes last night when I was working. So there are things that are the standard path for courses. And so it's about whether I go that far in that direction when I get to these things. You did talk about the remainder term for a Taylor polynomial, right? Yes. So see how I've said here that Taylor polynomial is equal to, all right? Taylor's theorem, so I've not given you a full statement of Taylor's theorem, all right? There's a whole pile of conditions and stuff that have got to be met and so on and so forth, right? And I have not tried to talk about that at all. But there is Taylor's theorem talk about the remainder term. And so this is the Rn of x. And we would say it's like the nth plus 1 derivative. Evaluated it, I'm going to say z because it's easier to write. X minus a to the n plus 1 on n plus 1 factorial. So what we've got is, this is pretty much what the next term of the Taylor polynomial will say. So this is actually the beauty of what Taylor actually did. We had this idea about creating polynomial approximations. But one of the things that Taylor's doing is he's going, actually, I can choose a z. So z, we say between x and a. All right. So doesn't matter which side of a x falls. So x is a is the point you expanded your Taylor series around. All right. So centered at whatever. There's a lot of ways of talking about that value a that we're centering our Taylor polynomial. We expand the Taylor polynomial about x is equal to 3. That's saying a is going to be 3. It's centered at x is equal to 3. That's telling you a is equal to 3. There's lots of ways of telling you what that value should be. Sometimes they will literally say, in the notation from the course notes, a is equal to 3. All right. So we will talk about that in different ways, and we will expect you to understand that that's what this thing means. And so we're going to go, there is some value of z for which this is true, all right, for which this equality holds, all right. I can choose a z such that this will be true. My problem is I can't tell you what that z is, all right. So I'm sure you had Stuart Johnson as your regular lecturer for this course. I'm sure Stuart Johnson would have told you about things like Taylor polynomials are the things your calculators use to actually calculate functions. Your calculator gives you an approximation. All right. We all know about pi, right? What we know about pi is an approximation. So some Japanese guy used what is it? It's like Fuji supercomputer. So I only know from 2011. I haven't actually checked recently. He calculated 2.6 trillion digits of pi on this supercomputer, right? But 2.6 trillion digits of pi is still just an approximation, and he is using. I'm gonna butcher it a little bit and just go. It's basically like a Taylor polynomial, right? There is a whole lot of other stuff going on in there. Originally based on a Taylor polynomial, stuff happened. Let's not try and go into it. So this is tremendously powerful techniques. And this remainder term is the reason we can say we've got that level of accuracy. All right. We can say, hey, this remainder term is this small. Therefore, this thing is accurate to that level of that number of digits. All right. So, so that's how we know how accurate we've got this thing. All right. And so what you would do, right? So I might go, hey, we've got sine of 1. All right. From my Taylor polynomial, what's my error bound? All right. How big could the error be? And so if I've chosen my n to be equal to, I'm going to say 4, so I've chosen a 4th order Taylor polynomial. Then I go through and put these things in. So this is like the 5th derivative. 5th derivative of sine would be a cosine. But, so this thing here, so my R4 of 1 would be for sine, would be this bit would be minus cosine of z. And then this will be x to the power 5. Actually, we're going to say 1 to the power 5 because that's the value 5 factorial. Okay. This thing here, so I don't know the value of z that's going to be the right number. There is definitely a value that would make this true, but I don't know what that number is. And so what I have to do is I have to go, I'm going to choose the value of z that makes that as large as possible. All right. And in this case, so z has to be between 0 and 1. Doesn't really matter. 0, cosine is 1. Cosine is never getting bigger than 1. So I'm going to replace this with 1. I'm actually going to go, the absolute value of this thing is less than or equal to 1 times 1 to the power 5 on 120. And so I know exactly, I can know that this thing is accurate too. If you actually were to do this, right? So 2 decimal places back. If you were to actually do this though, you'll find that it's way more accurate than that. All right. But this creates a bound. All right. And a bound for an error, thank you, is actually really useful. Okay. Now, this is the thing where I go, I can keep talking for longer if you guys actually got more questions. This is officially when this session is supposed to finish. But you know, like it's either talk to me here or talk to me up in the drop-in center. Phil, would you like to continue is probably the question we need to ask. Do you have more questions you would like to ask? Do you have somewhere you have to be? Yeah. So look, we're available in the drop-in center. Regular, so this week will be 10 a.m. to 4 p.m. Please come and ask us questions. Next week, so you said the exam is not Monday next week, or Wednesday, you reckon? Okay. It is your job to check that detail. I do not know. I do not get told that information. But next week, we're going to be open from 1 till 4. All right. But if you're having problems with something, there's the Maths Learning Centre email address, mathslearning@adelaide.edu.au, which you can get from our website. And you can always email us and we might. So, for example, you have to run off to work in the afternoons and you want to talk to us about something, we could arrange to talk to you in the morning for a bit so we can answer your questions, assuming we're free. Thank you so much for your attention. This will be uploaded to my uni course page, along with the scribbles that I've made. Okay. Thanks, guys. Good luck with the exam.
You're going to be in the drop-in center, the Maths Learning Centre.
Yeah, we'll be out after this. So, it turns out that my colleague made a slight error with some of the publicising, so I'm going to trot back to you at about 11:30.
Right.
If you're in the drop-in center, I might go and go. Just because because he sort of mistakenly put down the timeline in one place, we might come back. Yeah.
Okay. And where is the drop-in?
Oh, don't you know?
No, not off the top of my head. I normally go to the one just in the RW.
Okay. So
So
I'm gonna stop sharing. Just okay. So we're going to end the session here.